So in the last class we have discussed steady state response. Okay, so in steady state response, this is what the conclusion is, what we got. So up to this point is clear, all of you? I think unit ramp is what we covered, right? Can you hear me? Hello?
Yes, sir.
Yeah. So steady state, so this is the steady state error formula. Right. So this is what we discussed in the last class. ESS is equal to 1 by 1 plus Kp, and ramp input is 1 by Kv, and parabolic input is 1 by Ka. So I think ramp input is what not we covered. So now let us revisit what we did in the last class. So this is a second order system, right? So then we are trying to analyze steady state error. So when we try to analyze steady state error, so we try to derive the expression for E of S. So we got E of S by R of S, or E of S is equal to R of S by 1 plus G of S. Is it not?
Yes, sir.
So now steady state error is a limit tends to 0 S E of S. Right. So when you try to do it this, so limit. So now only one thing we did consider is parabolic. So limit S tends to 0. S E of S is R of S by 1 plus G of S. For parabolic input, what is R of S?
One by S cube.
1 by S cube. So when you substitute this, you are going to get limit S tends to 0. Right. This is 1 by S square plus S square G of S. Is it not? And ESS is equal to 1 by Ka, where Ka is equal to limit S tends to 0, S square G of S. Is it fine? Any questions? క్లాస్లో ఉన్నాను నేను 11 కాల్ చేస్తాను. Yeah, tell me. Hello?
Yes, sir. Yes, sir. No, I mean, no questions.
Yeah, fine. So now ESS is 1 by Ka, where Ka is S square G of S. So Ka is called acceleration error constant. Acceleration error constant. So in the last class, we have seen steady state error constant for unit ramp input as 1 by Kv, where Kv is given by what?
Velocity
Limit S tends to 0 SG of S.
Limit S tends to 0, SG of
SG of S.
This is Kv, velocity error constant. Similarly, when input is a step, what we got is ESS is equal to 1 by 1 plus Kp, correct, no? Where Kp is equal to limit S tends to 0, tell me.
G of S.
G of S. So this is what we got. So this is what it is written over here. Steady state error is 1 by 1 plus Kp, and it is 1 by 1 plus Kv, and then a parabolic input when you try to give, then you are going to get 1 by Ka, where Ka is limit S tends to 0, S square G of S. Right. So now for type 0 system, when you consider, this is what the conclusion we made. When input is type 0 and then system is type 0 and input is a step signal, then you will get a error constant, right? And if it is a type 1 system, static error constant is infinity, error is 0 is what you get. If it is a type 2 system, then static error constant, position error constant is infinity, and then error is 0. And similarly, ramp input also, when you try to consider, when it is type 0, kv is 0 means error is infinity, right? And when it is a type 1 system, error is means no, velocity error constant is constant, and then error is also constant. Means what? If you have an input of unit ramp, then there is a constant error throughout the response of the system as t tends to infinity. Means this error is constant, right? And then now here if you consider kv is infinity and error is 0, ready? Yeah. So when kv is infinity and error is 0 means your output will follow input, means there is no error. Input and output, as t tends to infinity, okay, as t tends to infinity, right? So the output follows the input, meaning is that. And similarly, parabolic input is steady state error constant is 1 by Ka, and for type 0 system, yeah, for type 0 system, for type 0 system, we may take Ka as 0. This, I think you can do it. It's not a big issue, right? So, and then error is infinity. And for type 1 also, when input is parabolic, error is infinity. But for type 2 system, the error is constant. Means what? If the input is going like this, a parabolic, right? So output will be going something, right? So error will be infinity. Input will be going somewhere, and then output will be going somewhere. You will get infinite error. So this is what we try to see from static error constants and system type. So now let us try to take a control system is given like this. To find the steady state errors for inputs of 5u of t and 5tu of t and 5t square u of t by first evaluating the static error constant is the what problem given. So when we try to analyze the error constants, remember first we analyzed it, the derivation which we used, E of s is equal to R of s by 1 plus G of s is the derivation by considering it is a unity feedback, correct? Yes or no?
Yes, sir. Yes, sir.
So when you consider this as E of s by R of s, then we will try to take this as open loop. G of s is a open loop transfer function. So when we try to evaluate the error constants, we have to take open loop response or transfer function. So now here, if you try to consider which type system it is,
Type 2, sir.
no,
Type 0.
Type 0, sorry.
No second order.
it is a type 0 system and second order system. So this is what open loop response. Okay, it is what open loop response. Right. So now Kp is what? Limit s tends to 0, G of s is position error constant. When you try to do, what you get? This one. When S tends to 0.
20.
122 by 3 into 4, right? So is that fine? Okay. So then KV is limit S tends to 0, SG of S. So what is KV?
0.
0. Right. And then what is KA? Which is S square G of S. KA is also 0. Okay. And then when KP is 20, steady state error is, okay, steady state error is 1 by 1 plus KP, right? And now the input here is not unit step, it is 5, right? Okay.
Yes.
So it is 5 by 21. Okay. Right. And then similarly here it is KV is 0. Ramp, steady state error when ramp input is means infinity. And then here E ramp is also infinity. So now let us take this is 5-8 problem in Quo. Right. So now tell me, find the position, velocity, and acceleration error constants. What do you do? First, you have to take open loop. So when you are considering about steady state error response, you have to take open loop response. Right, because the expression which we have taken is E of S by R of S. So open loop, not closed loop response you have to take. So G of S is equal to what? 5 into S plus 1 by S into S plus 2 into S plus 3. Correct, no? So what is the type of the system?
Sir, 5 into S plus 1 by S plus 2 into S plus 3 only, no, sir. Extra
5
S.
into
Why do we get a extra S in denominator?
this is there, no?
Sorry, sir. I didn't see.
Okay, so it is which type system?
Type 1.
Is type 1. Right. So if you have that table, it is very important. IES point of view, gate point of view. Okay. So if you try to see your previous exam papers, then definitely will be getting 1 or 2 questions on this. Right. So it is type 1. Now KP is what? Limit S tends to 0, G of S. So what is KP?
Infinity.
Infinity. And what is steady state error?
0.
Hello? Hello?
You are audible, sir.
Yeah, see, battery can, it can dry out any moment, right? So, I forgot my power supply in my cabin, right? So now let us try to do how much we can do, right? So ESS is 1 by 1 plus KP. So this is 1 by 1 plus infinity. So what is steady state error? 0. Means what? When input is a step signal, right? And if it is a type 1 system, then your output and input. Now let us take, you have done like this, right? So after some time, what happens is input and output both will be same. Okay. Meaning is that. And what is KA?
0.
Ka is
0, sir.
limit s tends to 0 s g of s. 5 into s plus 1 by s into s plus 2 into s plus 3. When s tends to 0, what you get?
Sir, Ka is s
KV,
square.
Huh?
KV.
Sorry. KV. So KV is
5 by 6.
5 by 6. So then steady state error is? Means there exists a constant error. And what is Ka?
Zero.
What is steady state error? That means what? When input is like this, right, your output may be like this. Infinite error. So this is what it is plotted here. So you can see the screen, no?
Yes, sir.
Yeah. So when roots are real roots, when zeta is very much greater than 1, God. Wait. So when zeta is very much greater than 1, overdamped system means slowly it takes response, means slowly it reaches output. And so which type of system it is? Overdamped. Which type of system it is? Critically damped. When zeta is equal to 1, you will get same roots, no? Critically damped. Here yesterday we have seen this. And this is underdamped. And this is
Undamped.
undamped. And this is the root lies on right half of the S plane. Means you give in unit step input, you will get exponentially increasing output. For finite input, we should get finite output, but it is infinite output. System is not stable. The roots are lying on the right half of the S plane. So simple example, g of s is equal to 1 by s minus 6. Now let us take this is a transfer function. Right. So let us take this as a transfer function. C of s by r of s is equal to 1 by s minus 6. Okay. So now let us take R of s. You can take impulse response. Okay. R unit step response. No problem. 1 by s into s minus 6. So what is C of t? 1 by s in a by s plus b by s minus 6. Okay. So here you will get like unit step means you will get 1, and here what you get? Inverse Laplace transform of 1 by s minus 6 and 1 by s plus 6. What do you get? Oi. Am I audible?
Yes, sir.
Yeah. So if it is s minus 6, in last classes we have seen it is s plus 6, e power minus 60 is what we used to get, no? So here
Yes,
what
sir.
we get? You will
E
get
power minus 60 plus
here
60
if it is minus means what we get here?
plus 60.
Et means for finite input we will get exponentially increasing, right?
Yes, sir.
So system is unstable system, right? So that is what the conclusion is. Now let us go ahead, right? So this is what the response is. Now this is what a problem. So this problem find the steady state error for the system input by taking x is equal to 5 by 2s minus 3 by s square plus 4 by s cube. What do you do? You try to take this as g of s, right? Open loop transfer function. And here x is equal to 5 x1 of s minus 3 x2 of s, 5 by 2 x1 of s and minus 3 x2 of s plus 4 x3 of s. X1 is when input is step, no? X2 is when input is ramp. And x3, 1 by s cube. Right. It is 4x3s or it is 2x3s? Tell me. Unit ramp input. What is the mathematical model? T square by 2 or t square or 2 by t square or what? Quickly. Oi. So here now when you try to take, here, this is what x1, x2 and all you can get. So summation of effects of individual inputs. So 5 by 2 steady state error, 3 by 3 and then 4. So E step is 1 by 1 plus Kp 0. E ramp is 1 by Kv 0. E parabolic is 1 by 2. Right. So it is, steady state error is 4 into, anyhow this is 0, this is 0. 4 into 1 by 2, 2. Steady state error is 2. This is what you can try to do similar problems, by taking the second unit is what it is considered. Right. So, and so you can solve the problems. Okay, you can solve the problems of 2O. So you have n number of problems, 5-13. The block diagram of a control system is shown. So I can ask any question in book or out of the book. So are you coming after mid-examination to the institute? Sai Varun? Varun? Anyhow, institute called back students. So whether you are coming or not, Dheeraj, you can respond. What is
Hello,
meant by hybrid mode, Varun?
Sir, hybrid mode is like it's like half of the students will be in the class live and other students can attend to their hostels.
Okay, right. And exam will be offline or online?
Exams will be offline, sir.
Then it's a good decision. Yeah. So if exam is on offline, if it is online, that is my wish. I can give questions from anywhere I want because it is like open book system, right? Yeah. So I think mid examination is open book system only, no, Varun? So I am telling you,
Yes, sir.
follow QO exactly. I will not deviate from QO. Right. So this is the problem. The block diagram of control system is shown in figure. Find the step ramp and parabolic error constants. The error signal is defined to be E of t. Find the steady state errors in terms of K, KT when the following inputs are applied. Assume that the system is stable. That you can do, I think. It is similar problem, 5-13. So how many problems you want? Those many problems are there. wide varieties of problems, wide varieties of problems. Okay. Stability is what I need to cover, but I'll be doing little later. So this is up to the second unit here. So if you have any questions, you can ask me now. In second unit, if you have, first order system, second order system, if you have any questions, you can ask me. So here are the questions then. Yeah, so I think few of you are asking questions, you are by mailing. So mostly I'll be, replying your mails. Okay, so if you have any questions while solving the problem, you can ask me, or you can mail me, no problem. Okay. So here, few problems are there. I think. So you can start from this particular point, fifth unit. Yeah, so determine the step ramp input like that, and then here, I think few of examples are given like here. Yeah. So can you see this 5-B problem? 5-2B.
Yes, sir.
So which type system it is?
Type 1.
I
Type 0.
type 0. There is no pole at origin, right? Okay, fine. That is one point. Another point, there is an exponential term, my e power minus 0.2s. Right. So any idea, any one of you, how can we write e power minus? Can any one of you tell me what is the exponential series? Exponential series here, expansion.
1 minus 1 by 0.2s plus 1 by 0.2s whole square.
Yeah. So when you expand it, what we try to do is, okay, what we try to do is we try to approximate it to the first order. So can we write this as 1 minus s tau if 0.2 is tau? Okay.
Yes, sir.
So that the way we can go ahead. So generally, and then one more point is, sir, in real time we may come across different systems, but only second order system is what you are discussing. Then what about the higher order system? So there is some very there is small what we can say, there is a so small 1 or 2 minutes discussion. If you have questions, I can answer your questions, or otherwise, I think I can take up a small topic. So MATLAB is only not covered. So definitely I'm going to cover MATLAB after this. Mm, So when you try to see the time response analysis of systems, so this is what we have seen. So here you have the different examples. So this is what we have seen. So this is critically damped system. This is also we have seen. Yeah. So coming to the higher order systems, what we try to do is, see now, it's a very important small topic only. So now you have transfer function. You may have 1, 2, 3 to 4 poles. So here you have two complex conjugate poles, and then four, here another two complex conjugate poles and two real poles. Right. So now here, if you try to consider the response of the system, okay, there is a region called dominant region. So what do you mean by dominant region? If the poles are lying very nearer to the S plane, and those poles will contribute in transient response like anything. So this region is called dominant region or dominant region. The poles which lies in dominant region is called dominant poles. Right. So if the poles, if they are lying very nearer to the imaginary axis, contribution of that will be in transient response.
Sir, can you once again repeat the definition of a dominant region?